What's that? Yeah, grab them. Time is up, you guys. Don't fold it. Don't fold it. Don't fold it. Time is up. Time is up. You're done. It's not fair to everybody else. You guys are doing a lot more time. Here's it in. Okay, so Here we go. Ready to start? So this relates to your quiz question number 2. Here's the height function. And I want you just to, there's a second line, it's going to graph the height function. And have we talked about how apostrophe will graph the second graph? Use apostrophes on your x and y. It opens up the second graph window on the right. So we're going to graph the height function in the right graph window. I've set up a slider for delta x, and then I've defined the left x function. Okay? So that's kind of the setup here. These lines are going to graph, so what we're after now is the approximate height function, and an approximate rate of change function. Okay? So what you guys are going to do to review is, so in order for those to graph correctly, they have to be defined. So those are not defined yet, and that's your job. So are you guys, do we remember from Friday? You're going to take a couple minutes, see if you remember how to define the approximate rate of change function in one expression. And don't just look at your notes and copy it down. So think through it again. See if you can figure it out. And then the approximate, so this is new now. What will the approximate height function be in one expression? Okay, see how you can do. Go.
I have no idea what's going on right now.
Okay, can you work with somebody else? I want to do some stuff on here. started. So if you have any value of x, the input's x, we want the output to be the average rate of change for in that current interval, right? And so we know we need these coordinates of these points. So so given a value of x, the coordinates of this point at the left end of that current interval will be left x, and in this case, h of left of x. So that's helped to get you started with both of these. Keep going, see if you can do it. Okay, any questions on the coordinates of those points? That's review. Hopefully you got that before I wrote it. How many people got it before I wrote it? Not enough. Okay, so you got to learn that, understand what's going on here. So for any value x, that average rate of change that we want is a matter of the two endpoints, right? And so you got to have those endpoints for any x. So we take left of x, and then the function value at left of x. And then on the right side will be left of x plus delta x, and h of left x plus delta x. So now, how do we define then the average rate of change for that blue segment given this current value of x? What's the average rate of change in general? So how do we get the average rate of change then? Change in y over change in output over change in input, or change in y over change in x. And so you've got your final height, your initial height, your final x value, and your initial x value. And you're going to find the change in height over the change in time. So that looks like this. There it is. Any questions? That's review. So the only difference is now I'm calling the function h. I think we called it little f before. On Friday we called it something different. Today we're calling it capital H. Okay, so where am I going to graph that? Is that going to be the blue segments? Is that the graph of the blue segments? No, it's not the blue segments. What is it? Rates of change. It's constant rates of change. Average rates of change, which we know are constant rates of change. So you're going to get this positive. If x is between 0 and 0.4, you're going to get a negative value in this current value, current interval. And then in this interval, you're going to get a greater negative value, right? So it's going to be positive, small negative, bigger negative. And where would it be appropriate to graph that? This is the rate. This is the approximate rate, so it makes sense to graph it over on the I don't know what's going on there. Hold on a sec. Okay, there we go. So this was what you should have sketched on your quiz. You've got a positive rate of change first, positive average rate, then a small negative constant rate, and then a larger negative constant rate. So that would have been your, on number 2, that would have been your sketch, 2E. Would have looked like that. Sketch for 2E. This would have been your sketch for 2B. The blue over here would have been your sketch for 2B. Okay, so then the question is, now that we have those rates, we can kind of, so the process that we're thinking through is exact accumulation, approximate accumulation, and then approximate rate of change, and then exact rate of change. But in creating the functions, the order kind of flips a little bit. When you create the functions, in order to create this approximate rate of, or approximate accumulation function, you need the rates to do that. So it's kind of like when you actually create the functions, the approximate rate function comes first, and then you use that to write this approximate accumulation function. But the process that we're thinking about is exact accumulation, approximate rate, exact rate. So now we want to write, this is new now, so now we want to write the exact accumulation function, this one that I've drawn in blue. Can you do it in one expression? Okay, so you've got the rate function, you've got the constant rates. Can you write an expression that will graph what I've sketched over here on the right in blue? It's nothing new. It's just applying what we've learned. See if you can do it. Go. Trying to write the approximate accumulation function. I'm calling it H1. H1. What's that? All x. It's a function. All x's. For all x's. Everyone get it around you? They all get it around you? Oh, I want this.
That would be the integral of the exact rate.
I want it this way.
Okay.
Too confusing, right? These are approximate functions, so we're not going to use integral. So we want point slope form, right? Point slope form. Okay, I'm going to come around. I'm going to see people that you got it. You're not just going to sit there waiting for me to have the answer. So I want to see. Where's that point slope form? Where's my point slope form? No numbers involved. You're writing a function or the whole thing. Yes. Yes, right. You will. It's going to change, right? Okay, what is point slope form? So we all should be able to write this down. Not A. X minus A plus B. That's it? Or K, if you want K. K or M. All right. So what will M be? What will M be, or K? For any X value? R1. R1. Okay, R1X. That's M. Okay, X is our current value of X. What's A? Left X. And what's B? H of left X. That will graph this whole thing in one line. Okay, so there it is. Graphing the, what is it? So H1x is our approximate accumulation function. I got it in this over here. This is the linear function that's like purple, pink. And then the blue one is the corresponding approximate rate function. And those are defined here. So just putting together tools that we already have. This isn't anything new. Just putting together, applying the tools that we already have to this new situation of starting with approximate, or starting with accumulation, and trying to figure out what the rate is. Okay, so how's our rate function? Is it pretty accurate? No, how can we make the, so now if we've got approximate rate and we want exact rate, delta x smaller. So every time I make delta x smaller, I get a better approximate accumulation function and a better approximate rate function. Now that the accumulation functions almost look identical, and here is delta x of 0.01, and the approximate rate function, which is a step function of all these little approximate average rates of change. Each one of those is an average rate of change. Is beginning to look a whole lot like a line. Okay? And so then imagine that delta x gets even smaller and we have our exact rate function. Okay, so let's go back to the area example. And just review the process one more time. We've got exact area. So this is the area of a square, okay? Area of a square. So x, the input is the side length of the square. Output is the area of the square. Here's our exact area function, x squared. And then from there, we build an approximate area function, which has constant rates of change. So that's why we needed average rate of change, so that we could get constant rates of change to approximate, to help us approximate that area function. And then we just take those values and we graph them as a step function as our approximate rate. And then we let that delta x get smaller and smaller. And so that's still approximate rate, just with very small delta x. And so we see the exact rate function starting to take form. Okay, so for this, let's continue on kind of with the area example, and let's talk about any questions about what we're doing. Yes, sir.
The other question I have is, when you get the approximate accumulation,
Uh-huh.
how do you determine the lines in between them? Where you have them on your graph, how would you determine where they're going to be and how far they're going to be between like variables?
So delta x, so
Right there, like the first line, how are you going to determine where it starts and stops?
delta x. So here delta x is 1. So our a value would be 0, and delta x is 1. So that would be our first segment.
Right, but it doesn't matter like where it's kind of, which way degree it's placed, what angle. It's just
No. So this segment comes from points on the original curve. It comes from the original curve. So those 2 points are points on the original accumulation function. We're going to join a segment, and so then the slope of that segment will be the average rate of change for that delta x. So those segments are determined by points on our original curve. Does that answer your question? Are you sure? Yeah, so that approximate accumulation function is coming from a delta x, and then once the delta x is set, it's coming from points on, in this case, the blue curve, the original blue accumulation curve. So it couldn't be anything else. Here's the point 1, 1, 0, 0. It can only be that segment from 0, 0 to 1, 1. And then from 1, 1 to 2, 4. Is it better?
Yeah.
Really? There it is. Okay, so we've been talking about this thing where we let delta x get small, and we say close enough that we can't tell the difference. That's what we've been saying so far. So we want to formalize that mathematically. This idea of close enough so that we can't tell the difference. So this is the idea of limit, okay? This is the idea of limit. We've been talking about limit all along, we just haven't said it as such. And so if we formalize that mathematically, this idea of close enough that we can't tell the difference, that's the idea of limit. So limit is like a never-ending sequence. So here we got in the elevator here. Where is she actually standing? Right there. Okay, so you see that if the mirrors were exactly parallel, this would go on forever, right? And so the never-ending sequence is kind of part of the idea of limit. Okay, so agree or disagree? If A and B are different numbers, then we can always find a number between them. For instance, their average. Agree or disagree? Agree. Right, if they're different numbers, we can always find a number between them. For instance, their average. Okay, agree or disagree? If the symbols A and B each represent a real number, and it's impossible to find a number between them, then they must be the same number, A equals B. If it's impossible to find a number in between them. Agree or disagree? Okay, well you can disagree, but it's true. If you can't find a number between two real numbers, then they must be the same number. So whoever disagreed, do you want to share why? Someone here? No? Okay. Just being cute, probably. Okay. All right, so 0.99999. 9's forever. That represents a number, right? So find a number that's between 0.99999 going on forever and 1. Can you find a number that's between those two? That's greater than this and less than 1. Can you do it? Tell me what it is. Some people are nodding their heads. What's that? No, but this goes on forever. Tell me a specific number. So the 9's just go on and on and on. They never stop. So is there a number that's greater than this one and less than that one? No, there's no number in between those. You can't tell me a number, and if it's less than 1, then it's greater than this. No, if it's less than 1, then it's also less than this. Okay? So therefore, since there's no number between them, like you told me in number 2 there, this number equals 1. Again, if you disagree, then all you have to do is give me a number that's greater than this one and less than this one, and I'll give you an A+ in the course. Just write out the number. Write it out. A number that's greater than this and less than this. There's a number between them, and then that would make that false. That would make that statement false.
Yeah, I'm just gonna get like
So this is the idea of limit. Okay? If we take the limit, this is the limit as n approaches infinity. So this number on the left can be written as this sum, the limit as n approaches infinity, of 9/10 plus 9/100, etc. As n just gets increasingly large without bound. So this whole thing right here, this limit as n approaches infinity, that's this number 0.99999. 9's never ending. And that the limit of that is equal to 1. Those are the same number. Okay. You got your homework for Wednesday? And we'll pick it up here.